And so today was the big event. It involved key companies responsible for giving driverless cars their eyes, their unique vision known as LiDAR.
A hurricane partially uncovered a mystery object in Florida.
A recent technological breakthrough has pulled back the veil on an extraordinary geological enigma hidden beneath Florida's dense canopies and swamps. LiDAR mapping, a remote sensing method that uses light in the form of a pulsed laser to measure variable distances to the Earth, has revealed a mysterious formation in the Sunshine State that challenges long-held assumptions about the region's geological history. Deep beneath what was once assumed to be a uniform stretch of sedimentary flatland lies a sprawling and unexpectedly intricate structure that seems to defy the geological norms traditionally associated with the southeastern United States. Before we start, smash the like and subscribe buttons for more updates. The discovery came as part of a broader LiDAR initiative aimed at improving flood models and assessing erosion risk zones across Florida's low-lying terrain. Scientists were stunned when the high-resolution topographic data began showing subtle but persistent anomalies just beneath the surface in a sparsely populated inland area of northern Florida. Instead of the predictable pattern of limestone karst topography, the dominant feature throughout the region, the LiDAR scans depicted an elaborate network of sharply defined ridges, deep depressions, and what appear to be unusually angular subterranean formations stretching across tens of miles. This unexpected discovery has instantly caught the attention of geologists, hydrologists, and even planetary scientists, many of whom are now re-evaluating previously held ideas about the state's formation. The defining trait of the newly uncovered feature is its distinct geometric shape, contrasting sharply with the gentle erosion-based curves and dissolution features typical of Florida's landscape. The linear ridges and depressions suggest tectonic activity or ancient fault lines, which are extremely rare in this part of North America. Florida has long been considered tectonically stable, a passive margin far removed from the dynamic boundaries of shifting plates. Yet the newfound evidence hints at a possible buried fault system or even the remnant of an ancient uplift, possibly dating back tens of millions of years. What elevates the intrigue is the lack of surface clues. Florida's thick vegetation, flat terrain, and porous ground often obscure subtle shifts in the earth beneath. Without LiDAR, it's likely this phenomenon would have remained undiscovered for decades, if not centuries. The technology's ability to penetrate tree cover and strip away surface clutter digitally has allowed scientists to view the ground as never before. And what they found suggests that the state's geological story is far from over. It may in fact be undergoing a fundamental rewrite. Among the more provocative implications is the possibility that Florida was once shaped by forces similar to those at work in more geologically active regions like the Pacific Northwest or the Appalachian Mountains during their formative eras. If the linear depressions and ridges found in the LiDAR data are indeed tectonic in origin, it may mean that the Florida platform experienced far more dynamic crustal movement in the past than anyone suspected. This could reposition the peninsula not as a stable geological afterthought, but as a once vital piece in the shifting puzzle of North America's prehistoric terrain. Further complicating matters is the feature's unusual orientation. The structure runs diagonally, cutting against the grain of known regional formations and sedimentary patterns. This alignment does not conform to the current understanding of sediment flow from the Appalachian uplands or the marine processes that have shaped the coastline for millions of years. The angles and symmetry in the subsurface topography are striking enough that some researchers have tentatively compared them to buried rift zones, where continental crust once pulled apart, or even to remnants of ancient impact craters deeply eroded and obscured by time and sediment. Adding to the mystery, the LiDAR scans revealed evidence of subsurface voids and collapsed chambers at regular intervals along the ridges. These features resemble neither sinkholes nor typical cave systems. Instead, they suggest a deeper, more complex process at work, possibly a history of underground fluid migration, magma movement, or buried mineral veins that have long since altered the surrounding rock. Some scientists have posited that the geometry of these depressions might align with deep-seated structural weaknesses in the Earth's crust, dating back to the Mesozoic era or earlier. Such a timeline would drastically extend Florida's active geological past and link it to continental processes that are still poorly understood. The implications extend beyond geology alone. Hydrologists are now studying how this newly revealed structure may be influencing groundwater flow and aquifer recharge in the area. Florida depends heavily on its vast underground aquifer system for drinking water and agriculture. Any previously unrecognized structural influences on water flow could affect everything from drought resilience to contamination pathways. If these ridges and depressions act as conduits or barriers for water movement, the consequences could ripple across policy, urban planning, and environmental protection. Moreover, archaeologists have taken a keen interest in the discovery. The LiDAR mapping project that led to the geological finding was initially part of a broader effort to locate early human habitation sites in Florida's interior. The subtle surface variations seen in the data often signal buried ruins or land use changes from prehistoric cultures. While this particular anomaly proved to be natural in origin, its complexity has inspired a renewed focus on how terrain shaped early migration and settlement patterns in ancient Florida. The alignment and positioning of high ground relative to water flow and resources may have influenced how prehistoric populations moved across the landscape, hunted, and established permanent or seasonal settlements. At the heart of this discovery is the power of LiDAR to act as a geological X-ray, unmasking the ancient skeleton beneath Florida's sandy skin. Where aerial surveys, satellite imagery, and ground-level observations had failed to penetrate the mystery, LiDAR's ultra-fine resolution and penetrating capabilities succeeded. What it unveiled was not merely a curiosity, but a monumental shift in how we view Florida's past. The data collected is now feeding into sophisticated 3D models that aim to reconstruct the region's subsurface architecture in unprecedented detail. These models may eventually help determine the origins of the anomaly, whether it is indeed tectonic, magmatic, or something altogether different. The timing of this revelation could not be more critical. As climate change increases the frequency and severity of storms, Florida faces rising sea levels, saltwater intrusion, and land subsidence. Knowing more about what lies beneath the surface could offer new strategies for resilience and adaptation. For instance, understanding how subsurface ridges redirect or contain groundwater might inform future water management systems, helping to preserve freshwater supplies amid intensifying pressures. Likewise, if the formations turn out to contain mineral-rich deposits or rare geological materials, they could hold economic as well as scientific value, though such potential would need to be weighed carefully against environmental concerns. In a broader scientific context, this find serves as a potent reminder that even in regions considered well understood, the Earth holds secrets just beneath our feet. Florida, long dismissed as a geologically quiet zone, has revealed a glimpse of an ancient drama frozen in stone. The very notion that hidden tectonic structures or long-forgotten rift zones could lie undisturbed for eons, only to be uncovered by the sweep of a laser from above, reshapes the way scientists approach flat vegetated terrain worldwide. This realization is already inspiring similar surveys in other seemingly unremarkable locations, in hopes of uncovering what else might be hidden in plain sight. This revelation also underscores a turning point in the use of remote sensing technology for Earth science. While satellites have long played a role in mapping and monitoring environmental conditions, LiDAR represents a deeper level of investigation, one that can reveal microtopographical features with centimeter-level accuracy. The Florida discovery is a testament to this capability. As more regions undergo detailed LiDAR scans, the expectation is that Florida's buried mystery may be just the first of many. Entire layers of geological understanding once hidden by vegetation or dismissed due to lack of visible clues may soon come to light, rewriting textbooks and challenging scientific dogma. At the same time, this unfolding narrative highlights the importance of interdisciplinary collaboration. It was only through the combined efforts of geologists, remote sensing specialists, archaeologists, and environmental scientists that the full scope of the anomaly began to emerge. Each brought their expertise to bear on the puzzle, interpreting the data from different angles and revealing a story far more complex than any one discipline could tell alone. This cross-pollination of ideas is paving the way for a new era of Earth science, where technology acts not just as a tool for observation, but as a catalyst for holistic understanding. The sheer scale of the discovery continues to grow as more of the area is mapped, Preliminary estimates suggest the geological structure extends across nearly 100 square miles, with varying depth and complexity. In some areas, the formations dip hundreds of feet below the surface, suggesting a process of uplift and erosion that spanned millions of years. Radiometric dating and core sampling efforts are already underway to pin down the age and composition of the underlying rock. Early results point to an unexpected mix of materials, igneous, metamorphic, and carbonate layers, interwoven in a fashion not typically associated with Florida's sedimentary crust. These findings hint at a possible origin rooted deep in the Earth's mantle, or perhaps linked to continental fragments that predate the Atlantic Ocean itself. As scientists piece together the timeline, the narrative becomes richer and more mysterious. Did this structure play a role in ancient sea level changes or climate shifts? Could it have been part of an island chain, an elevated ridge above sea level at some point, hosting ecosystems long since lost to time? Fossil hunters are now joining the effort, combing the vicinity for traces of ancient marine or terrestrial life that might offer clues about the environmental conditions during the formation's rise or fall. Whatever its origin, the structure's discovery is an invigorating moment in the ongoing story of Earth's hidden history. It's a vivid example of how much more there is to learn, not in the distant reaches of space or the ocean's abyss, but right beneath our feet. Florida, known for its beaches and retirement communities, has suddenly emerged as one of the most fascinating geological frontiers in the United States. And at the center of it all is LiDAR, a quiet flickering laser mapping from the sky, illuminating not just the surface, but the buried truths of a continent still full of surprises. The technology has opened a new window into the past, revealing that beneath even the most familiar terrain may lie ancient stories waiting to be uncovered. For Florida, this is not just a curious anomaly, it's a tectonic revelation in more ways than one. The magnitude of what LiDAR mapping has revealed in Florida extends far beyond the contours of a single geological formation. As scientists continue to process the data, they are beginning to appreciate the significance of the broader structural context in which this feature is embedded. This is not an isolated anomaly, but may be part of a much larger system that spans the southeastern portion of the United States, hinting at a complex and interconnected network of subterranean dynamics that have quietly shaped the region over millions of years. Early interpretations suggest that the newfound formation might be linked to ancient crustal boundaries, relic scars from supercontinental breakups that occurred hundreds of millions of years ago. These scars, known as suture zones, are where continental fragments once collided or drifted apart. In Florida's case, the subsurface geometry identified by LiDAR could be a remnant of the time when North America was joined with what is now Africa and South America during the era of the supercontinent Pangaea. As Pangaea split apart, segments of landmass were stretched, fractured, and ultimately covered by sediment. The structure uncovered by LiDAR may represent a piece of that ancient rupture, long buried and only now emerging through the veil of time. What makes this possibility particularly compelling is the apparent consistency in the angle and orientation of the formation relative to known tectonic boundaries of the Paleozoic and Mesozoic eras. This formation could represent a transitional zone between continental and oceanic crust, a rare and scientifically valuable feature for understanding continental drift and plate tectonics. Researchers are now exploring whether seismic reflections and gravity anomalies in this region support this hypothesis, using the LiDAR discovery as a starting point to integrate various geophysical data sets in new ways. The implications for plate tectonic theory are substantial. Florida has long been considered a passive appendage of the North American plate, largely shaped by sedimentary processes, with minimal influence from deeper Earth dynamics. But this discovery challenges that categorization. If further evidence confirms that the structure originated from deep crustal or mantle-related processes, then Florida's role in the plate tectonic history of the Americas will need to be re-evaluated. It could mean the peninsula is underlain by ancient crust far older than previously assumed, perhaps a microcontinent or terrain that drifted and docked during early Earth history, carrying with it a legacy of geological complexity. Moreover, the newfound formation could serve as a natural laboratory for studying deep-time processes with real-world relevance. Understanding how such structures form, how they evolve, and what materials compose them can offer insight into modern-day concerns such as geothermal activity, mineral resource potential, and subsurface fluid migration. There is growing interest in whether this structure contains mineralized zones, particularly rare earth elements or metal sulfides that often accumulate in geologically complex regions. While commercial exploitation is not yet a focus, the potential for future discoveries is there, especially in a world increasingly dependent on high-tech minerals for batteries, electronics, and green energy infrastructure. Beyond the geological and resource-related implications, the discovery is reshaping how researchers understand Florida's climate and environmental history. Geological formations influence everything from soil chemistry and plant distribution to atmospheric circulation patterns over millennia. The elevation changes and underground voids revealed by LiDAR could have altered drainage patterns, influenced river courses, or even acted as climate refugia, zones that retained stable environmental conditions during periods of regional climate upheaval. These areas may have sheltered plant or animal species through dry spells or ice ages, allowing pockets of biodiversity to persist in ways previously unrecognized. Ecologists are now teaming up with geologists to examine vegetation patterns and wildlife distributions in the area around the anomaly. Even subtle changes in topography can have profound ecological effects, influencing microclimates and habitat boundaries. If the ridges create slightly cooler or wetter conditions, they could serve as hotspots for unique flora or fauna, possibly even species not yet cataloged. In this sense, the geological discovery may trigger a wave of biological research, further expanding the circle of disciplines touched by the LiDAR revelation. In parallel, hydrologists and engineers are turning their attention to how the formation might influence stormwater dynamics and floodplain behavior, critical issues for a state frequently battered by hurricanes and tropical storms. The subterranean ridges may act as barriers that force groundwater to surface in unexpected places, or redirect floodwaters during heavy rainfall events. Mapping these underground features allows engineers to better predict how water will move during extreme weather, and could inspire new strategies for constructing levees, canals, or artificial wetlands designed to work with, rather than against, the land's hidden contours. For coastal planners and emergency managers, this level of precision offers a potential game changer. With climate models predicting increased rainfall variability and sea level rise, having accurate information about subsurface geology will become essential for resilient infrastructure design. Entire cities could benefit from updated risk maps that incorporate the influence of these newly discovered features on water retention, drainage, and soil stability. Insurance companies, too, are taking note, considering how this discovery could inform new risk assessments or policy pricing models for properties located above or near these formations. On the academic front, the LiDAR discovery is fostering a renaissance in Florida-focused geoscience. University departments, research institutes, and independent think tanks are pivoting resources to launch studies that would have been inconceivable just a few years ago. Proposals are being drafted for long-term drilling programs, high-resolution magnetic surveys, and deep core analysis. These efforts aim to extract physical samples from the most enigmatic parts of the formation, bringing to light the textures, compositions, and isotopic signatures of rocks that have not seen the light of day in hundreds of millions of years. Students and early career scientists are being drawn into the project with a sense of enthusiasm rarely seen in regional geology. For them, this is a chance to contribute to a once-in-a-generation discovery. The excitement is not merely about solving a puzzle, but about exploring an entire new dimension of a landscape they thought they knew. Field camps, previously centered in more tectonically active zones like California or the Rockies, are now being planned in Florida. Drone mapping, ground-penetrating radar, and remote data modeling are converging with hands-on fieldwork in a comprehensive effort to decode what this LiDAR anomaly truly represents. While the focus remains scientific, the cultural and educational impact is also beginning to resonate. Museums and science centers across the state are planning exhibits dedicated to the find, eager to share the story with the public. Florida's image, often associated with tourism and retirement, is being reimagined as a place of deep-time wonder, where ancient Earth processes have quietly sculpted a complex, unseen world. For younger generations, this narrative could spark a deeper connection to their local environment and inspire new interest in science, technology, engineering, and mathematics. The broader message reverberating from this discovery is that Earth's most fascinating stories often lie hidden in the least expected places. Florida's flatlands, once considered geologically tame, have turned out to be anything but. The power of technology, in this case the high-resolution precision of LiDAR, has brought into focus a feature that has rewritten maps, models, and theories. But perhaps more importantly, it has rekindled a spirit of exploration and inquiry. Every new dataset, every model iteration opens another layer of questions. Was this feature ever above sea level? Did it influence sedimentation during the formation of the Gulf of Mexico? Could it connect to similar structures in the underwater continental shelf? If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Florida's LiDAR mystery? What do you expect was found? We want to hear from you. Thank you for watching, and see you next time.